Okay, so now we're going on to the next topic. And that is particle kinematics. That part isn't new, but now we're going to 2 dimensions. And we know that in 1D and 2D, most of the important quantities that we deal with are directional quantities. When you have values in those quantities, they tell you something about a direction as well as a magnitude. So we need directional quantities in 1D and 2D. In 1D, so, think about an object moving along a line. And let's say that the object is right here. The thing that characterizes 1D is that at any location, you only have 2 choices of where to go. Okay, so this particle can go this way or this way, and that's all of its choices. So if you choose a positive direction, one of those directions can be, by your choice of the positive direction, one of those 2 directions is defined by positive and one's defined by negative. So since there's only 2 possible directions, you can give the direction by assigning one way positive and one way negative. Okay, that works out perfectly. There's 2 signs and there's 2 directions in 1D. But now everything is going to get screwed up in 2D. That's a nice system. In 2D, if you have a particle here, it can go this way or this way, or this way or this way, or anything in between any of those. Okay, so at any location, a particle has infinitely many choices of where to go. And so obviously the positive, negative sign isn't going to give us a direction anymore. There's no way to specify infinitely many directions with only 2 signs. So that won't work. In 2D. So we need something else to specify directions. And the thing that we're going to use to give directions in 2D is called a vector. And so now, before I get back into 2-dimensional kinematics of particles, I have to spend, probably we'll get done today or close to the end of it today, but I'm going to spend today giving just bare bones definition of what we need for trigonometry, and then using trigonometry to define vectors. And then those vectors are what we're going to use for our calculations. Okay, so that new thing is vectors. And you can think of a vector as an arrow. In space with two properties. So let's say this is a vector. Okay, an arrow. This is what I mean. It's not just a line. It makes a distinction between one side, the side with the head, and the other side with the tail. Okay, so a line doesn't make a distinction between this and this. This one is this way. And the two properties that this vector has are magnitude. That's the length of the arrow. And the second one is direction. That's the way the arrow is pointing, where the head of the arrow points. And notice that, number in one dimension had these same two exact properties. Had these same two properties. So for example, if you have a velocity of -6 meters per second, yes. Yeah. Well, no, it's not a ray because because the length of the arrow matters. So you'll have short ones and long ones, and those give the magnitude. Yes. Okay, so if you in 1D have a velocity of -6 meters per second, that means you have a magnitude of 6 meters per second, and it's pointed in the negative direction. Okay, so in 1D, a number, so in other words, a number is really, you can think of it as a 1D vector. I didn't really think of it that way much, but it has the same two properties as a vector, and that's a fine way to think about it. All of our directional quantities will be vectors in 2 dimensions. So we're talking about position, displacement, velocity, and acceleration. And when we define something as a vector, when we have a quantity that's a vector, we're going to indicate that by putting an arrow over the top. That's a vector symbol. So position, displacement, velocity, and acceleration are all vector quantities. notice they all have different units. So the vector itself doesn't have its own units. The units depend on what kind of quantity it is. Just like in 1D, a number didn't have its own units. It depended what you're talking about, velocity or acceleration. And so this is, it doesn't what?
It doesn't have the units of velocity.
Yeah, it is. So the vector, well, I suppose you could think of it as a vector number times units, the same way as you think of like a number. Yeah. Yep. So so like a velocity vector, we'll talk about it as like components 2, -4 meters per second. So it will have units, the same way like a directional quantity in 1D had units. Okay, so let's look at this example here. We do calculations with vectors. We're going to express them in component form. We're going to talk about the components of a vector. And to come up with components, you need to first choose a coordinate system. So once you choose a coordinate system, you can express the vector using components. So the way you can think of that is if this is the coordinate system, here's your x-axis and there's your y-axis, and this is the vector. We can break that up into, so if you think of traveling from the tail of the vector to the head of the vector, you can do that in 2 legs of the trip. One that's parallel to the x-axis and one that's parallel to the y-axis. Okay? And those 2 separate legs are going to be called the components. How far did you have to go in the x direction? And did you have to go in the positive or negative x direction? And then the same thing for y. Yep. No, not really, not yet. But you can get slope information of the vector off of the component information, and we will talk about how to do that. Yeah. Okay, so let's think about the components of this. So in order to get from the tail of this vector to its head, you go this far along the positive x direction. So we'll call this the x component. What? Well, we're not going to use the rise. You can think of it as a rise and a run. We're not calculating the slope right now. You could. And then the second leg is like from here to here. And that's called the y component. And you can see that these 2 legs of the journey are always going to be perpendicular to each other. And so if you draw the vector and then you draw the 2 components like this, it's always going to make a right triangle. And that's why trigonometry is going to be important in this. So to calculate components, this is a set of steps that'll always work. So for a vector with a length L, capital L. So the first thing you need to do is put the tail of the vector at the origin of the coordinate system, where the x and y axes meet. I'm going to talk about coordinate systems a lot, so I'm going to start abbreviating it just CS. Whenever I write CS, that's what I'm talking about. Then the next step is to determine the counterclockwise angle from the positive x-axis to the vector, and we're going to call that angle theta. Yeah, it has to be the positive side of the x-axis. I'll do a couple examples. Um, then the x component is L times the cosine of theta, and the y component is L times the sine of theta. Yep. And we're going to write this. So our component notation for vectors will be, so if this is the vector u that we're talking about, the variable is u and the arrow says that it's a vector variable. We're always going to put the x component on top, so L cosine theta. Underneath, we're going to put the y component, L sine theta. And we're going to use square brackets around them. And notice that's not a fraction, so there's no bar between them. It's just a way of writing the two components. And it's sort of a concise way to write it. You don't have to say that this is the x component. If you put it on top, we know that it's the x component. The y component is always on the bottom. So this top one is always the x component. The bottom is the y component. And there are a lot of different ways, a lot of different notations for writing the components of vectors. This is the one we're going to use in this class. But it doesn't change the meaning of any of this stuff to write it a different way. You can come up with your own where you draw a monkey and then the x component sits on the monkey's head and it's holding the y component, and that would work just the same, you know. But this is the notation we're going to use. So let me do an example. So let's say that we have a vector that points this direction, and it has a length of 5. And let's say that this vector makes an angle with the vertical of 45 degrees. And we're going to calculate the components of this vector in two different coordinate systems. So the first one we're going to use is the standard coordinate system that I'm sure everyone is most used to working with. And then after that, we're going to calculate the components of the same vector in a coordinate system oriented like this, where this is the x-axis, this is the y-axis, and there's an angle of 45 degrees between the vertical and the y-axis. Yeah. Yep. Although, if I didn't draw the negatives, then if I just drew it like this, then I'll tell you later why you would know which one was X and which one was Y. Yeah, exactly. That's right. Okay, so magnitude's 5. That's going to be our L. And for each of these, we just need to figure out that angle theta. So let's do this first one. So the first one, our coordinate system looks like this. The first thing we do is draw our vector, and the vector is fixed in space. We don't rotate this vector. It is what it is. You know, it has its own identity. We want to respect its identity. So I'm going to draw the vector with the same length and the same orientation, but with its tail the origin of this coordinate system. Okay, so there's the vector. And now you can tell if you look at how I define the vector, it makes an angle of 45 degrees with the vertical. And this coordinate system has the y-axis on the vertical. So we know that this angle between the y and the vector is 45 degrees. Okay. And so now what we have to do is figure out that angle theta. And to figure out theta, we start at the positive x-axis and figure out how far we have to rotate counterclockwise to run into the vector. Okay. So we're going to start like this. If we rotate 90 degrees, we're like this. Yep, and then 45 degrees more, and we're at 135. So theta for this is 135 degrees. And so then the components of this vector, I'll call it u again, are equal to, so for the x component, it's going to be the length of the vector, 5, times the cosine of 135 degrees. So 5 times cosine of 135. And the y component is going to be 5 times the sine of 135 degrees. Be sure you have your calculators set in degrees. Our angles are all going to be in degrees in this class. Yes, because cosine is the x. Okay. Okay. So if you plug that in and you have your calculator set in degrees, this will give you negative 3.535, positive 3.535. And what that says is, that's the x and the y component. So that says to get from the tail of the vector to the head of the vector, you first go along the x-axis, along the negative says you go along in the negative direction. You go a distance of 3.535 along the negative x, and then you're there. And from there, you go in the positive y direction, another 3.535. Okay, so in that first coordinate system, these are the components. Now let's do it for the second coordinate system. Anybody have any questions about that yet? Yes. All really the only thing you're going to have to do in problems is just come up with the components. I'm just trying to sort of keep illustrating what it means, you know, because it's sort of a new concept. But that's what the negative there means. If that was positive, then to get from the tail to the head means we would go that far in this direction before we went up. You get a different vector. So the new coordinate system is like this. There's the x-axis. There's the y-axis. And we know that it's a 45-degree angle from the vertical to the y-axis. So in this coordinate system, where does the vector go? So remember, we don't change the orientation of the vector. We just sort of overlay, think of overlaying the vector picture you have on top of the coordinate system. Yeah, so the tail goes at the origin. And now the only way to interpret this is that the tail is at the origin and the vector lies right on top of the y-axis. Okay, so first let's do it. Yeah, that was just the coordinate system I chose. We could have lined it up so they were a little different or whatever, but that's the way I chose it. So let's first do it with that angle theta. Okay. So remember, to get that angle theta, you have to start on the positive x-axis, and then you have to rotate counterclockwise from that to the vector. So what's the angle you have to go starting at this x-axis to get to the vector? Yep, 90. So theta is equal to 90 degrees. And so that means that the vector components are 5 times the cosine of 90 degrees. That's the x component. 5 times sine of 90 degrees. That's the y component. And that just gives you 0, 5. Because the cosine of 90 is 0. Okay, so the reason I did this one where the vector lays right on top of the y-axis is that whenever you have a vector that lies right on top of either the positive or the negative axes, you don't have to calculate that. You can just go straight to the vector, because if you're trying to come up with a path that goes from the origin to some point along the y-axis, okay, you can't go anywhere along x and then go y to get there. The only way you can get there is, in this case, start here, skip the part of going along x, and then just head out along y. So if you know the length of the vector, in this case it's 5, you're just gonna go 5 in the direction of that axis. And if instead that vector went along the negative y, it would be 0 for the x component, negative 5 for the y component. Okay, so any of these 4 axes, if you have a vector that along x, along y, along negative x, along negative y, you can just go straight to writing that down. That's, you know, L0 or negative L0 or 0L or 0 negative L. Yep, yeah, I could have chosen a different coordinate system for that where this was along the negative x-axis, just like rotated 90 more degrees and then, or 90 degrees that way, and yeah, yep. Okay, so now here are some things to notice about this. Some things to keep in mind. First, we've seen something like this before, and it might not be totally obvious, the connection on your own, but this choice of coordinate system, so choosing the orientation of the coordinate system is the two-dimensional equivalent of choosing the positive direction. Okay, so where we used to have to choose the positive direction and then that specified the negative direction, and then we could assign numbers to things. Now we have to choose an orientation of the coordinate system. And there are going to be times, you know, the majority of the problems we do are going to just use normally the standard coordinate system. But there are going to be problems we do that are going to be easier if we use a funky rotation of the coordinate system. So we're going to do it sometimes. Yes. Yeah, however you want. The only rule, and I'll get this in your notes later on, but the only rule is you can't flip it. So we're going to keep it. So anywhere you can, if you start with the standard one, anywhere you can rotate it is fine as long as you don't do this and then rotate it. And the second thing to notice is the components of a vector, or let's say finding the components of a vector is exactly the same thing as finding the coordinates of the head of the vector when the tail is at the origin. And one way that's useful is you can use that to sanity check your answers. Because once you draw your coordinate system, however it's oriented, this is the first quadrant, this is the second quadrant, this is the third, and this is the fourth. And notice that, you know what the signs are of the coordinates of any point in this quadrant, and you know what they are in any one of those. And so if you have a vector that if you put it at the origin, it would point into the first quadrant. What sign does the x component have? Positive. And what sign does the y component have? Good. And in the second quadrant, x, negative, y, positive. Third, x, both negative, yep. And then the fourth, x, positive, and negative. And so if you think of putting the tail of the vector at the origin, then depending on which quadrant the vector points into, those are going to be the signs of the components. Most likely, if you do a calculation and the signs of your components don't match the signs that you should have according to this, your calculator is in radians and you need to switch to degrees. That's the most likely thing that would go wrong. Any questions about that? Okay, so that's how we calculate components. So once you have your vector expressed in component form, there are three types of calculations that are going to be useful to us. The first one is adding two vectors. The second one is multiplying a vector by a number. And when you're talking about a number as opposed to a vector, that's called a scalar. So I'm sure I'll say that by accident some. So that's what it means. When I say multiply a vector by a scalar, it just means one thing is a vector, one thing is just a number, and you're multiplying them together. And then the third thing is calculating the magnitude of the vector. Okay, so the first one, adding two vectors. So if you're adding one vector that has components A, B to another vector that has components C, D, the sum of those two vectors has an x component that's equal to the sum of the x components and a y component that's equal to the sum of the y components. And that has a physical meaning to a graphical meaning that you can imagine. We'll talk about this graphical meaning more in lab. But this is how we do the calculations. But I'm going to call this a physical meaning. Of adding two vectors. So the first step is put the vectors head to tail. And then the sum, or it's called the resultant, has its tail at the free tail. I'll show a picture of what I mean. And its head at the free head. Okay, so for example, if you're adding this vector plus this vector, you put the tail of one at the head of the other one, and it doesn't matter what order you choose. Okay, so I imagine taking this one and moving it over here so the tail is at the head of this one. Any questions about what I did there? I could have done it in the other order too. It doesn't matter. You get the same answer either way. Tail to head. As put the vectors head to tail. And then this, okay, so all I've done so far is put the vectors head to tail. I haven't done the second part yet. And then the resultant vector goes from so the free tail and the free head. Like this tail and this head are touching, so they're not free. But this is the free tail, this is the free head. So the resultant vector goes from here to here. So if this is like, if you call this U1 and this is U2, then this one is the sum, U1 plus U2. And it turns out that this simple way of doing the math works exactly like if you really carefully took measurements of the length of these vectors and measured the angles with protractors and did this thing and then measured the angle of the resultant with a protractor and a ruler. You get the same thing doing this as you do with this. Okay. This is the way we're going to use for calculations, but this is the way to kind of imagine how it works. So let me show how that works with a example. So let's say we have the vector 5, -5. And the vector 0, 4. So to add them, you take 5 plus 0. That gives you 5 for the x component. -5 plus 4 gives you -1 for the y component. And so that's the sum of those vectors. That's the resultant vector. Now, let's think about the directions of these vectors and do this addition graphically and see if we can, hopefully if we do it carefully enough, we'll be able to convince ourselves that it's the same thing. Okay, so let's use this coordinate system. So first, this vector 5, -5. That's, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this 5, -5, we go in the positive x direction 5, then the negative y direction 5, and so we're right at this point here. And that's the location of the head of the vector when the tail is at the origin. Our first vector looks like that. And then our second vector goes 1, 2, 3, 4. Goes 0 in the x direction, 4 in the positive y direction, so it's right here. That's the head, so we're adding these two. And so now if I add those two sort of carefully, so we have that one, and we put the tail of the second one at the head of this one. And then the resultant goes from the free tail to the free head. We get something like that. And now if we think about the components of that one, draw this over here. Then that vector would be, you'd go 5 in the positive x direction and 1 in the negative y direction. And that matches the answer we got here. Okay. So those are the same thing, those two ways of doing it. It's not really that surprising. I sort of drew the picture to make it work, but yeah, if you did it really carefully with a protractor and stuff, it would work out exactly. Yeah, that would have been a good idea. I wouldn't have had to draw so many pictures. Yes. Yep. Yep. Okay. So that was, yes. You'll do problems where you'll be given that something happens at 30 degrees above the horizontal, and you have to use that fact to calculate vector components that'll then go into the calculations. Okay, the second kind of calculation we're going to do is multiplying a vector by a scalar, by a number. And mathematically, when you do it in components, that isn't like adding, it's an easy calculation. So if you have a vector AB and you want to multiply it by the number C, you do that by, so the X component is going to be the number times the X component, so that'll be C times A. And the Y component will be the number times the Y component, so that's CB. That also has a physical meaning that's pretty easy to wrap your head around. So the physical meaning, we're going to think of it in two parts. So the first one is if you to multiply a vector by a positive number, um, so what you do is keep the vector in the same direction. Keep the vector in the same direction. And multiply its length by the number. Its magnitude is multiplied by the number. Okay, so for example, if you're multiplying 2 times the vector, so let's say the vector we want to multiply is this. And the way you do that is you keep the direction the same, and you multiply the length by 2, and then that will be the output vector. Um, that way of thinking about it is for positive numbers. So the other thing we need is we need to know how to multiply by -1. So to multiply a vector by -1, keep the length of the vector the same, and just switch the head and the tail. So for example, -1 times this vector is this vector. And so now with those two things, in 2 steps you can do multiply by any number. Like if you want to multiply by -40, you first keep the length the same and keep the direction the same and multiply the length by 40. And then when you're done with that and you have this long thing, then you just switch the head and the tail to make it negative. Well, yeah, I mean, when we're doing this physical stuff, so I guess the key thing to remember is that we put the tail of vectors at the origin in order to visualize certain things, and but a vector doesn't have a position. It only has 2 properties. It only has a magnitude, a length, and a direction. And so you can move vectors around in space. Um, so when you're talking about an individual vector, it doesn't matter if it's heads at the origin or whatever, or tails at the origin or whatever. It's you move it over so the tail's at the origin to do certain calculations. So I think that's probably a fine way to think about it, but yeah. Okay, and let me do an example of a calculation. So if you want to multiply 8 times the vector -4, +6, then the x component you get out of that is going to be 8 times -4, so -32. And the y component is going to be 8 times 6, so 48. And if you had this vector's tail at the origin, what quadrant would its head be in? 2. That's right. Because you have a negative x component and a positive y component. And if you multiply this now by -1, which quadrant would it be in? 4, it would just switch to the opposite direction. But mathematically, you can just think the x component would be positive, the y component would be negative, so that's the 4th quadrant. Yep. I think that's a nice way to think about it, yeah. Oh, yeah, sure. Yeah, I mean, I think, yeah, think about it as coordinates. I mean, really, what coordinates are is the vector from the origin to the location. So there's really no distinction between coordinates and components. You're just used to talking about coordinates, and you haven't done calculations with vectors yet. That's the only difference. This is in the 2nd quadrant, and if you multiplied that by negative something, it would be in the 4th quadrant. Yes. Yes, that's right. Yeah, so that's what multiplying by a -1 always does, reflect across the origin. Yeah, it's just reflected straight through the origin, not about the x-axis. You know what I mean? But I think you're thinking about it right. Any other questions? Okay, there's one more calculation that we're going to do, calculating the magnitude of a vector. So sometimes you have the magnitude and an angle, and you have to turn it into components to do calculations. Other times you have components and you need to figure out the magnitude. It's just nice to be able to go back and forth. So to calculate the vector magnitude, so if your vector u has an x component of A and a y component of B, then the magnitude of the vector, which you write as the absolute value, so the absolute value symbol for a vector means the length or the magnitude, is equal to the square root of A squared plus B squared. That formula probably looks familiar. Can you place where that formula is from? Pythagorean theorem. Yep, and it's not just a coincidence. It really is the Pythagorean theorem that we're talking about here, because if you want to know the length of this vector, given that its components are A and B, that's a right triangle, and the length of the vector itself then is this. Okay, there's only one more thing I want to say. Well, let me do a calculation. Okay, so let's say that our vector u is where was that? Okay, so let's say that our vector u is -3.5 3.535, positive 3.535. What's the magnitude of that vector? So that would be, so square negative 3.535. The negative goes away when you do that. And add that to the y component squared. And take the square root. 5. And the reason I did those numbers was because the first example we did started with a vector with a magnitude of 5 somewhere here. It had a magnitude of 5. We went through those steps to calculate its components. So when we use those components to recalculate the magnitude, it needs to give back the original value. And so it does, it gives back 5. Okay. The last thing I want to say is, so we talked about the fact that these components are dependent on what coordinate system you use, but not any two perpendicular vectors are an allowable coordinate system for us. So the question is, what coordinate systems are allowed? And the answer is you can use any coordinate system. So start with that standard coordinate system that you're used to. And you can rotate it, but don't flip it. So like, for example, here, so this is allowed. This is allowed. But this isn't. And this isn't. Because both of these, if you start, so if my thumb is the x-axis and my first finger is the y-axis, you can start in that standard orientation and rotate it to get back. And this one you can do if you're really flexible. And that's still just a rotation. So there's no way to start like this and rotate it to get this unless you flip it. Same with this one.